This parachutist will reach a terminal velocity of about 50 meters per second. It will take them about 12 seconds and they will have fallen about half a kilometer. How do we explain terminal velocity using physics? Let's start by thinking about how we describe motion in physics. The velocity time graph is an important graph. It means that we have to be able to capture the velocity of an object at any time. Now I'll come back to the vector nature of velocity compared to scalar speed in a moment. The important thing to remember about the velocity time graph is its gradient will tell us about acceleration. And we need to be very clear about what acceleration means. The other aspect of the velocity time graph that we're going to need is the idea that the area underneath it between two times will give us the total vector displacement, or if we're just dealing with scalars, the distance travelled. The key thing to remember about vectors is that they are not numbers. We do have to be able to add vectors, but we've got to be careful. 4 newtons plus 4 newtons doesn't really have an answer, because Newton is the unit of force and force is a vector. We can use arrows to represent vectors, and the arrow is useful because its size will represent the magnitude and the direction relative to some coordinate grid, like the boxes that we have here. Now I can do the above addition. For example, if I represent the 4 Newton, this 4 Newton force by an arrow 4 boxes long in this direction, and I add to it another 4 Newton force described by this arrow, then the law of vector addition will say that this is 0 newtons. Velocity is a vector too, and we need to remember that as we talk about terminal velocity. One way to explain the behavior of mechanical systems is to use Newton's laws. Let's start with the first law. When I'm working with people on this sort of thing, we try and boil it down to its simplest essence, which talks about something called F. Please don't say that F is a force. We must always think about it as the result of the vector addition of forces. So it's called resultant force or total force or net force. And what Newton says is if there is no resultant force, then constant velocity is the natural motion. The second velocity then deals with what if there is an F, if there is a total force, if there is a resultant, then given a parameter called mass, then there'll be an acceleration, and the acceleration will be proportional to the size of F and in the same direction as F, because this really is a vector equation. Then finally, perhaps the most tricky one is the third law, and it's saying that we can describe interactions in physics by forces. So for example, if we think about two bodies interacting, and notice I haven't put them touching, they could be, but in this case, A is interacting with B, and what the law says is that the interaction of A on B, represented by this yellow arrow, is the same size as the interaction of B on A. It's the same size, but in exactly the opposite direction. We can think about a steel ball bearing falling close to the Earth's surface using the following model. So I represent the ball bearing by a particle, and I'm putting in one interaction. This is the interaction of the Earth pulling on the ball bearing. And we've learnt to write this interaction as m times g, where g is acceleration due to gravity. Analysing the velocity time graph for the ball bearing using the gradient and the area ideas, we can come up with a predicted curve for how long it will take for the ball bearing to fall through a certain distance. That's represented by this green curve. And if we make some measurements, we see that the data fits quite nicely on this predicted curve. Pause the video to think about this question after reading it carefully. Think carefully about the text circled. This question caused a lot of problems for GCSE students. Here we see the feather and the hammer at time 0 and a little bit of time later. The drag forces have become larger. We can consider a couple of models for drag. This one, which says that drag depends on some sort of radial distance and speed, and this one, which is pretty common on physics sites, which says that the drag is proportional to cross-sectional area and speed squared. The important thing to learn from the drag models is that drag depends on speed and on some dimension of the object. The hammer moving faster may be responsible for its bigger drag force when compared to the feather. What we learn from the drag models then is that the drag force, providing the shape doesn't change, depends on the speed of the object. Now, in this case, with the hammer and with the feather, the drag will be increasing as the speed of the object increases. The interesting thing, of course, is that because of the much smaller weight of the feather, the drag force can become equal to the weight at quite a low velocity. Whereas with a hammer, the drag force never quite balances the weight of the hammer. Of course, if the hammer was given enough height to fall through, eventually the two forces could come into balance and the hammer would reach terminal velocity. This animation was created in a free piece of software available online called Modellus. What we can see here is the growth of the drag force as time proceeds. We can also see a plot of the velocity time graph. So we are at terminal velocity of this purple curve, not quite terminal velocity on the red curve. The difference being the drag factor, which you can change in the model. By working in a modelling environment, you can try the different drag representations of drag, the AV squared or the RV model, and you can produce predictions from your model, which you can then compare with experimental results. Read this question carefully, study the graph, then pause to think about the shape of the graph. Notice that there are two terminal velocities, one at 60 meters per second and one at about 8 meters per second, and these need to be explained. To explain what's going on, we need to use, in this instance, Newton's laws. We have a drag force, which depends on some model of drag. Let's use the AV squared model for drag. We know, applying Newton's laws, that when the skydiver, represented as a particle, when its weight is balanced by drag, then the net force is 0 and the acceleration is 0, so velocity is constant. Now, we have the same force picture whether we're talking at 60 meters per second terminal velocity or 8 meters per second terminal velocity. We can balance the same weight by having a small cross-sectional area going very fast or a much bigger cross-section area going slower. Both these drag forces are equal to the weight. We've got the force diagrams which describe terminal velocity. Let's pause the video and try and fill in force diagrams for this section of the curve and this section of the curve. Try and do that now. You might end up sketching something like these pictures here. Think carefully about the following discussion. During this section of the motion, the acceleration is in the downward direction, and the velocity is in the downward direction. So the velocity is increasing. In this portion of the graph between the two terminal velocities, the acceleration now is in the opposite direction to the velocity. That does not mean the parachutist is moving up, but what it does mean, of course, is that his velocity will decrease in magnitude. Think about how these vectors explain how we go from 0 velocity to 60 meters per second and from 60 meters per second to 8 meters per second. Pause the video and think about this question step by step using a drag model. I would suggest that the AV squared model is a good one to use in this case. Here we see a question about another common terminal velocity scenario, a ball bearing dropping through oil. In this case, the distance time graph is being used. This curved portion of the distance time graph says something about the velocity. This straight line portion of the distance time graph says something about velocity. Stop the video and think about what the velocity time graph would be like and try and sketch it. This is what you should have found for your velocity time graph, something like this. And we can see pretty clearly a terminal velocity, which corresponds, of course, with this straight line portion of the graph here. And the curved portion says that this is again note distance time graph would infer that the acceleration of the object is getting smaller and smaller until it becomes 0 at terminal velocity. Be absolutely clear about why the velocity time graph is curved this way, and that this curvature infers that the particle, the ball bearing in this case, is decelerating. Let's do some explaining using Newton's laws now. So the little ball bearing will have an interaction due to gravity called weight. There will also be a pressure difference interaction, which we normally call upthrust. And also in the upward direction will be our drag force. And we have to use some drag model. Let's use AV squared, but probably for the ball bearing, RV would be a better model. Now we can follow through in our normal way explaining. The upthrust, which just depends on the volume of the ball bearing, doesn't change. The weight doesn't change, but the drag is changing in time. And as the ball bearing falls faster, the drag force will increase. Eventually, when we add the forces, the total force will be 0. And this will correspond to an acceleration of 0, which, following through our logical pattern, means that we are now at terminal velocity.